10.6 now. So 10.6 is all about alternating series. We've already looked at this a little bit. Alternating series is when the terms, alternate positive, negative. We're just going to jump straight into the test for this. So this is a theorem called the alternating series test. If you do have an alternating series, positive, negative, forever and ever and ever, or at least eventually positive, negative, forever and ever, we can see if this thing is going to converge. The steps for doing that is first, you have to think of your series as being written in a special way. So it needs to be written like this. Sum going from, it doesn't really matter what the starting position is, so either 0 or 1 or anything else to infinity. You have to have this -1 term out in front, so we're going to do -1 to the n plus 1, and then we're going to write it as u sub n. You want to think of this u sub n as being the sequence values where they're all positive, only that -1 is what's making it alternate. So if I were to plug in to be 1, 2, 3 into this, where to get the first sequence term, u sub 1, it would be positive. The next sequence term would be negative, the next one positive, and so on and so forth. Okay. So you want to think of those u sub n's as being just positive values. And in fact, that's going to be one of the parts to our test. So this converges if the following conditions are met. And there's 3 of them. So the first thing is that those u sub n's are all positive. Right? The next thing that has to happen, and this is usually the one that's the hardest to show, is that those u sub n's are eventually non-increasing. Remember, non-increasing, it's either staying the same or it's decreasing. Okay? The final thing that you have to show is that those u sub n's are as a series, a sequence approaching 0. And that's it. That's the only 3 things that you have to have for this series to converge. The u sub n's have to be positive, which makes it alternate. They have to be eventually non-increasing, in other words, decreasing. And you have to have that the sequence goes to 0. Okay, so just a quick example. We're going to look at the alternating harmonic series. So we've looked at the harmonic series before. The harmonic series is that series 1 over n. So this series is going to be the sum going from 1 to infinity of that -1 to the n plus 1 term out in front times 1 over n. Oh, not like that though. There we go. Okay, so for this example, my u sub n is going to be this 1 over n. They are definitely positive as n goes from 1 to infinity. Don't forget that this -1 to the n plus 1 is not included on the u sub n. The u is just the other part, so just the 1 over n, which is always positive. They are non-increasing, right? As my n's get bigger and bigger and bigger, this term is getting smaller and smaller. And as n goes to infinity, 1 over n does go to 0. So this converges by the alternating series test. Okay, so just a little bit more about this before we jump into another example is we have to talk about something that converges conditionally. This would be an example of something that converges conditionally. It only converges whenever it's alternating like this. So remember in the last section we had absolute convergence. This does not converge absolutely. It converges when it's alternating like this, but if you were to take this -1 term away, then you would just have the regular harmonic series, which remember diverges. Okay, so this does not converge absolutely. This converges conditionally because it only converges when it's alternating. Okay, cool. So let's look at a little bit more difficult of an example. Let's look at the infinite series 10n divided by n squared plus 16. Okay. Oh, sorry, and then the -1 term out in front. So -1 to the n plus 1. 10n over n squared plus 16. And we want to see if this thing, does this converge? Okay. You don't have to do the other tests if you have an alternating series. Just because the alternating series is a very useful and pretty easy test to use. The only time that you do need to use a different test is if you have to figure out if it converges absolutely, because the alternating series test is not going to help you out there. But if we just want to know if this particular alternating series converges, we can use the test. So it sometimes helps to write out what the u sub n is going to be. For us, the u sub n is going to be that 10n over n squared plus 16. All right. Then we just have to show the three things. First thing that we have to show is we have to show that my u sub n's are always positive. I hope you can see that this is true. It's pretty obvious to be true because if my n is going from either 0 or 1 to infinity, then every positive n that I plug in here is only going to get positive numbers. If it's something that's obvious like this, you don't have to actually write anything out to prove it. You can just state that it's easy or true. Okay, the next thing that we have to show is we have to show that these u sub n's are non-increasing. This one is not so obvious. So one technique that you can do to show this is by finding the derivative of your sequence and showing that the derivative is always going to be negative. Because if the derivative is negative, that means that your slope is negative, which means you are decreasing. So we will show this by showing the derivative is negative. All right, so that means we have to take the derivative of our sequence here. You can think of the sequence as being a continuous function since we're taking the derivative of it. Unfortunately, we're going to have to do quotient rule stuff. So it's been a while since I've done quotient rule, but I think it's bottom times the derivative of the top minus the top times the derivative of the bottom. That whole thing divided by the bottom squared. Great. Okay, so we want to simplify this down a little bit. So combining like terms and multiplying out the numerator, just kind of double check to make sure that you're getting the same thing I'm getting here. 10 times 16 minus n squared divided by that n squared plus 16 all squared. Okay, so remember that this is the derivative, and we want to know when is this derivative less than 0. So let's just set it to be less than 0 and figure out when that happens, or if it even happens. So if we set this less to be 0, this the denominator is doing nothing, right? The denominator is always positive. The only time that we could ever actually be less than 0 is if the numerator is less than 0. So let's just focus on the numerator being less than 0. What we can do is we can divide everything by 10, and then that's just going to really do nothing. So we get 16 minus n squared is less than 0. At this point, we would subtract the 16 over. So now we would divide by -1, but you have to be careful here because remember when you divide by -1, you have to flip the inequality over. So we get n squared is greater than 16, and then we can take the square root. I know that when you take square root stuff, you should worry about the positive and the negative, but we're not going to worry about the positive and negative because our n value can only be positive anyway because we're in this the series. This is the index, don't forget. So we get n is greater than 4. What this is saying, remember, is that this was us setting the derivative to be less than 0. Our derivative is less than 0 as long as n is greater than 4. But don't forget, if I scroll back up to our theorem here, 2 says that as long as the u sub n is eventually decreasing. This does decrease as long as n is greater than 4. So thus, we have shown that my u sub n is non-increasing for n greater than 4. Which is all we need, right? All we need is to show it's non-increasing eventually, which is what we've shown. So now 2 is true. The last thing that we had to show was that my u sub n as a sequence is going to 0. So let's look at my use of n's. The use of n's, don't forget, was this 10n over n squared plus 16. And we want to take the limit of this as n goes to infinity. And I hope it's pretty easy to see. You can think about horizontal asymptote stuff. I have this n squared in the bottom and then a 10n up top. You could also do L'Hopital's rule here. If you take the derivative of the top, you just get 10. If you take the derivative of the bottom, you get 2n. And if you take n to go to infinity, this does in fact go to 0. All right, so thus, by the alternating series test, our series converges. We do not know if it converges absolutely, therefore we can't really say anything else except for that it converges. Great. So that's the alternating series test. There's just one little thing that I want to show you. It's only going to take a minute, so I'm not going to make a new video for this. The other thing that I want to show you is that you can also use alternating series to do some approximations. So this theorem is called the alternating series estimation theorem. And there's some pretty cool math behind the scenes here. So again, I'd always recommend that you read through the book for this stuff, and they have a pretty cool proof for this as well. But this is what the alternating series estimation theorem says. If you do have a series n going from 1 to infinity of this same thing that we had before, the -1 to the n plus 1 and then the use of n, if you know that this converges. So let's say you already know that this converges to L, then that means that the partial sums would just be the u1 minus the u2 plus the u3 minus u4 plus, and it would go all the way to whatever use of n is, whether it's positive or negative, we don't really know. Okay, this partial sum approximates L to within an error of the absolute value of use of n plus 1. Okay, cool. So this is the theorem. The partial sum, whatever this partial sum comes out to be, approximates my limit or my sum to within the absolute value of the next term, use of n plus 1. The reason for this is because if you are alternating, that means that your sum is bouncing back and forth between the actual sum. Again, I'd recommend looking through the book to kind of see why that's going to be. So just a quick example of this. Let's say that you had the infinite series n going from 0 to infinity. That -1, we're just going to go to the n this time. The reason we're just doing to the n and not to the n plus 1 is because we're starting at 0 instead of starting at 1. And then we're going to do this of 1 over 2 to the n. Okay, we already know that this converges. This converges based on something that we did in the past of just 1 over 2 to the n. Since 1 over 2 to the n converges, then the alternating series of 1 over 2 to the n has to converge. So that was a theorem we saw in the last section. All right, we're just going to take n to be 8, and then we're going to find two things. First, we're going to find the partial sum s sub 8, so this would be adding up the first 8 terms of our series up top there. I'm not going to write it all out because I've already done this in my notes here. So if you add all this stuff up in the calculator, you get 0.6640625. The next thing that we're going to do is let's just go ahead and find what the partial sum would be if I did add in that 9th term. If I added in the 9th term, it would be 0.66796875. Okay, so what's important here on what that theorem up above is saying is that the sum is within an error of the next value. Well, we just added on the next value to my partial sum, which means that the actual sum must be between these two values. In fact, so this is to the side. There's no way of showing you this without doing some higher level math stuff, but the sum does come out to be 2/3, so 0.666 whatever. Okay, but that is what the alternating series estimation theorem allows us to do, is it allows to approximate the actual sum by just looking at the partial sum. Great.